Okay guys, in this video we're going to be looking at our formulas for compounding interest. And so we have two of them, as a matter of fact, and we really do want to distinguish between the two. But they're really just some plug and chug type of relationships. We're going to plug in a bunch of things we know and find maybe a desirable unknown, or maybe two desirable unknowns. So let's go ahead and start with this. We say that first things first, when we talk about compounding interest, again, remember that we're talking about something that at a certain point over time, it's going to grow as a certain percentage of itself. And so we say every time that it grows, it compounds. And what we have is n compoundings per year. That is a set number of times per year that it's going to grow as a percentage of itself. Or if we have continuously compounding things, continuously compounding. And that's really weird because continuously compounding is like a formula that would state that something is always growing as a percentage of itself every moment of every day. So we'll go ahead and start with our n compoundings a year. We say that the amount that we have, and we could really call this the amount as a function of time, really is this initial amount, which is our principal, times 1 plus the rate over n, where n is the number of times it compounds per year, to the nt power. And so in terms of what we have here, remember that A is the amount at a given time. Okay. P is our initial amount. We usually refer to this as our principal amount. But I'm going to write the initial amount, which is our principal amount. Okay. And then we have R as our rate. Let's just make sure that we use a decimal. Use a decimal. When we do our math with percentages, we do want to use decimal values. And then T is our time. And just to be clear in this, we're going to interpret time as being in years. And so with respect to this n compoundings per year, we have these 1, 2, 3, 4. I suppose 5 values here. There's one that I've left out. N. N. It's the number of times per year we compound. And so that is to say that if we said annually, we would say 12 times a year, that would be 12. Whereas if I were to say 4 times a year, that would mean like something like quarterly. Quarterly is, 4 times a year. So with all of this right here, we say, well, how does this compare to continuously compounding? The neat thing about continuously compounding, it is that it's a similar relationship, except for that it's always amount is equal to what you started with, times e to the RT, where e is just our natural base. And so we have these same 3 quantities here. So let's take a look at a couple that compound n times a year. We'll just do our plug and chug. I really want to talk about how you would get this into a calculator. So this won't take a long time. We say that using our formulas for compounding interest and for continuously compounding interest, determine the balance A for P dollars invested at a rate of R for T years and compounded n times per year. So with all of these, I usually find it's a good idea to list these out from a word problem, but because we have them listed here, we're going to go ahead and put this in, and what we were asked to find is the amount or the balance. So we're after the left side of this equation here. So we say our amount in this case would be equal to our principal. So we started with $1,500, and this would be 1 plus now our rate. Now our rate, what I'm going to write up here is this is a decimal is 0.02. And the reason why is because whenever you have a percentage, you move that decimal twice to the left to get the decimal value for the percentage. So we'd say this is 0.02, and this is all over n. Now, n is quarterly, so 4 times a year. And this is all to the nt. So in this case, we're going to get 4 times 10. So you'll notice how this is kind of really a complex expression to simplify here or evaluate. So I'm going to give you some advice today. First thing is, if you can rewrite your exponent as some whole number value, I'm going to do it. 4 times 10 is just 40. But what's in here, what I would do is I would start with what's inside the parentheses and get a decimal value. So that is to say, I could say, what is 1 plus, in parentheses, 0.02 divided by 4? And so what I end up with is this decimal right here that actually does terminate 1.005. But what I'm going to tell you is when you do these problems, sometimes this decimal doesn't terminate. You should still start on the inside of this. Now here's the number one mistake that you can make. A is not equal to, what would I get if I took this times 1,500? 1,500. Okay, 1507.5. This is not 1507.5 to the 40. Don't ever do this. You cannot multiply these two things before you do your exponents just because of, well, order of operations. And so this would be bad. Do not do this. What we want to do is, and we could just go ahead and do this by typing in here, this into our calculator, but what we want to do is we want to go ahead and do the 1.005 to the 40 first. And so I'm going to write approximately equal to, and we're going to type this in just like you see it. So 1,500 1.005 to the power of, and I could even write 4 times 10 as long as I do it in parentheses up there, or to the 40th power. So we get this about 1831.19, so we get 1831.19. And the important thing here to recognize is that we were talking about money, so your initial investment of $1,500 over the course of 10 years, compounded quarterly at a 2% rate, you've actually gained $331.19. So let's take a look at a different situation where maybe if we increase our rate, in this case, if we move our decimal to the left twice, we get 0.035, and we change our initial investment to be $2,500 and compound it monthly for the same amount of time, we should probably get a little bit more money. So we would say, starting with our initial investment, $2,500, we have 1 plus our percentage here as a decimal over 12, which is our number of times we compound. And this is to the NT, so 12 times a year for 10 years, that's going to be 120 total compoundings. So just like I did on the last one, what I'm actually going to do is I'm going to start by finding what's inside these parentheses first. And so what I'll do is I'll say 1 plus, and I get 0.035 divided by 12. Okay, so I get this, 1 plus that. So this big long decimal. So I'm going to rewrite it here. We have 2,500, and this is to the 120 power here. But this would be approximately 1.003. Now, what I'm going to tell you is do not use this 1.003. Don't use approximations until the last step. So what we're going to do is we're going to say that since this represents what's in the parentheses, the next thing I want to do is raise this, or take my answer that I just got, to the power of 120. And so by doing that, we get 1.003 to the 120. We get what we're going to take next times 2,500. So we get about 2,500 here. Not about 2,500. We get about this 1.418-ish. So I'm going to say that this is approximately 2,500 times 1.418-ish. Okay. But what we're going to say, though, is we get exactly 3545.86. So about 3545.86, and we definitely see that we got some more money from this investment just because we had a higher rate of growth and we compounded more times a year. So now for this last one here, you'll notice that it says principal $2,500. Rate, we'll go another 0.5% higher, 4%. We'll do 20 years, but compounded continuously. Now when you say continuously, what does this mean for you? Well, first of all, it means that we're going to use the natural base, okay? And this formula right here, this model. But it also means that it compounds every second of every moment of every day. Every moment it's compounding. And so because as n gets very large in this first formula, this part right here collapses or approaches e, we can instead just use this formula right here, PERT. So we'd say that my principal, 2,500, e to the power of RT, we'd say, well, my rate is 0.04, okay, times the time, which is 20 here. We get this expression that you see right there. And so this is as easy as we're just going to go put it into our calculator. And so we have 2,500, and remember that your e to the power of key is right here, e to the power of, we'll put 0.04 times 20. And what we end up with then is this number right here, about 5563.85. So about 5563.85 dineros. These are pretty easy to do as long as you know which formula to use and how to put it into a calculator. Cheers.